Hello, thanks for coming to the talk. I am Alan Wu from University of Washington. Today I'm going to present our paper called A Controllable Model of Grounded Response Generation. This is a joint work between UW and Microsoft Research. I'll start by introducing the motivation of this work. Our work focuses on the task of open domain response generation. Recent transformer-based models like Dialog GPT can already generate human-like conversations with impressive fluency and diversity. However, as the generated responses become more diverse and informative, they also tend to contain more hallucinated facts. To address the factual hallucination issue, adding grounding knowledge from external sources like Wikipedia or IMDb in the movie domain and so on can be a promising solution. Let me show you how grounding can actually help recognize correct content with an example. This example is intentionally selected to be about an entity that's not too well known, such that the model might not have seen it many times during the unsupervised pre-training stage. Here, the dialogue goes, do you know the 2020 presidential candidate John Delaney? And, oh, the congressman from Maryland. Remind me where he was born. Now, the model generates the next response to be Delaney was born in, which should be followed by a location indicating the place of birth. We measured the log likelihood of 5 common state names at the following decoding timestamp. The correct answer should be New Jersey, based on Wikipedia. The ungrounded version of our model, which I'll introduce later, falsely assigns the highest probability to New York. However, the grounded model that takes the text from Wikipedia as grounded knowledge assigns a much higher score to New Jersey, other than the others. However, grounded generation is not often effective. For example, grounding does not guarantee response specificity, and when the preceding dialogue is more open-ended, and there are many pieces of information in the grounding that fit the dialogue context, there's no specific basis for picking either of them. In this example, the agent is supposed to give some interesting details about the movie La La Land with access to the movie's Wikipedia page. The open-ended query, tell me more about it, makes it hard for the agent to decide which specific information to attend to. So it ends up saying, it is a 2016 movie, which is a quite bland response. However, if we could add control to enforce a certain level of specificity, the agent would be able to talk about more interesting stuff. In this same example, adding the lexical control phrase, Damien Chazelle, makes the agent generate more specific content. It is a musical film directed by Damien Chazelle, and Ryan Gosling is also in it. Motivated by the above observations, in this work, we propose to combine grounding and control into response generation. In specific, we propose a novel framework called Controllable Grounded Response Generation that generates a response for the dialogue context, lexical control phrases, and groundings. We consider 2 scenarios for lexical control of conversational text generation, where the control phrases are provided by a simulated user or automatically extracted by a control phrase prediction model. Next, I talk about problem formulation as well as the dataset we use in our experiments. The framework, Controllable Grounded Response Generation, is defined as given dialogue context X, lexical control phrase is C, which consists of a sequence of P lexical phrases, and grounding knowledge G, which consists of a sequence of Q sentences. We aim to generate a response R that contains semantic information guided by C, where C can be either directly provided by user or automatically derived from a control phrase predictor. We use the grounded Reddit conversation dataset from Ching et al. In our experiments. This dataset covers 178 subreddit topics, and each dialogue context comes with multiple reference responses. However, since we target to test our framework, which involves control phrases besides grounding, we create good control phrases by matching each reference response to grounding text. We only keep responses with at least one matched phrase. For details about defining control phrase, as well as phrase quality verification, please refer to our paper. we end up with a large enough dataset with over 400K utterances. The average number of control phrases per response is about 1.3. Here's a data point example in this dataset. The control phrase pancreatic cancer is defined by matching grounding text and the reference response. Next, I'll walk you through our model design for the CGRG framework. For the scenario where the control phrase is predicted, I'll introduce the control phrase prediction model as well used in our experiments. First, we leverage the recent progress in pre-trained transformer-based language models. Although a framework can be generalized to any attention-based model, we illustrate our method with the basic autoregressive generation model like GPT-2. We concatenate X, C, and G into a single input sequence S, and we train the model with the standard MLS laws, with the output to be the response R. Note that for the CGRG framework, we only use grounding sentences that contain one or more control phrases in C, and we denote this set of grounding sentences by GC. However, the fully connected attention could be problematic because some attention links are not necessarily relevant. For example, in this case, if we know that control phrase C1 is only found in grounding sentence S1, while C2 is only found in S2 and S3, then we may only want to keep attention links between C1 and S1, C2 and S2, as well as C2 and S3, if we look at attention at the phrase or sentence level. In addition, we remove attention across different sentences, as well as across different phrases. We call such predetermined attention links based on structural information between C and GC inductive attention. And we modify attention masks by setting undesired attention links to be 0 and the others remain at 1. By doing so, each layer in the model would have a more sparsely connected attention. The control phrases used as input in our CGRC framework can be provided by a simulated user. In this scenario, we use gold control phrases defined in our dataset for experiments. The control phrases can also be from an automatic control phrase predictor. We experiment with 2 different types of predictors. The first one is a retrieval-based model that, given a dialogue context X, selects the 2 most frequent n-grams in the top 50 sentences in G, ranked by IDF weighted word overlaps with X. The second one is a fine-tuned BERT QA model that predicts the top 2 string spans as the control phrases. It is fine-tuned using X as the query, G as the document, and gold control phrases in C as answers. Next, I'll present our experiment setup, results, and analysis. We use GPT-2, the small version, as the basic model for all transformer-based models in our experiments. Each transformer-based model is initialized with DialogGPT, which has the same architecture as GPT-2 and is the state-of-the-art model on Reddit dataset and is pre-trained on large-scale conversational data. We apply different type embeddings. For X, C, G, and R, we use greedy search decoding unless otherwise specified. We evaluate different models for response generation. GPT-2 and GPT-2IA are the models for the controllable and grounded response generation described in the method section, without or with the inductive attention mechanism, respectively. GPT-2 plus GBS also takes in both control and grounding. However, it takes control phrases as constraints at inference time only, with grid beam search decoding, which stands for GBS. Therefore, during training, it only takes grounding and dialogue context as the inputs. CMR is a previous state-of-the-art grounded model on the Reddit dataset that combines a MRC model and a LSTM decoder and does not take control. In order to analyze how control and grounding helps with the response generation individually, we also apply GPT-2 to evaluate on input settings with different combinations of control and grounding. We also test the input setting X plus GC, where G is filtered by C, while C is not provided explicitly in the input. We evaluate systems by both automatic and human evaluation. The human evaluation is used to verify the improvements of the best case systems as determined by the automatic metrics. And we observe reasonable consistency between automatic and human evaluation results in our experiments. Our automatic evaluation includes BLUE, NIST, as well as diversity of bigrams, which are all well-known metrics for response generation. BLUE measures n-gram match to references, and NIST is a variant of BLUE that assigns higher weights to more informative n-grams. They can be used to roughly measure response specificity and appropriateness. All these measures are higher the better. We ask human judges to measure relevance to the preceding dialogue, as well as consistency with the grounding on the 5-point Likert scale. For the first scenario that uses gold control phrases to simulate user control generation, we use single reference evaluation since different reference responses respond to different gold control phrases. Here, we show the automatic evaluation scores for different configuration of models and input settings. Comparison between line 1 versus line 3 and 4 indicates simply adding grounding or control to the model input improve the performance. Comparison between line 2 and 3 shows that pre-training and transformer help improve performance over LSTM. Line 3 or 4 versus 5 or 6 indicates combining control and grounding works better than adding either single one. Here are some more comparisons for the user-controlled generation setting. Comparing line 1 and 3 and 4 tells that providing control phrases in an explicit way is important. Comparing line 2 versus 3 and 4 tells that applying control in hidden states helps the model generate better quality responses than decoding only. And if we compare line 3 and 4, we see that inductive attention helps further boost the performance. Our human evaluation in relevance to dialogue context and consistency with grounding confirms that our CGRG framework with inductive attention overall outperforms other systems. For the second scenario, where control phrases are predicted by a predictor model, since predicted control phrases are independent of reference responses, we evaluate each generated response against multiple references with up to 5 alternative references and calculate the maximum score. We also hold out one response in each reference set as the human system setting to give more insights. We observe that both control phrase predictors with the CGRG framework achieve overall better performance than X plus GPT-2, which is the same setting as Dialog GPT. We also notice that NIST and BLUE scores are generally low, even for humans, partly due to the high diversity of plausible responses. And the crowdsourced human judges also confirms that our CGRG framework significantly outperforms X plus GPT-2. Here's a case study example that shows how grounding helps inhibit hallucination. Given the conversation as well as the grounding text about an education background of a person called Sam, we measure the token level log likelihood of a target response. He graduated from University of Toronto in 2017 with a master thesis about economics of neural networks, as shown in Figure 1. In this response, 2017 is factually correct. and the grounded model assigns a much higher probability to it, while master and economics are incorrect, and the grounded model gives much lower scores to them compared with the ungrounded model. In the same example, we output each model's assigned probability to the top 5 tokens plus a distractor token Canada in the grounding after generating the partial response Sam just graduated from University of. We notice that no grounding and no control gives equally distributed probabilities to well-known American state names. Adding grounding helps the model rank locations based on background knowledge. Further adding control helps the model locate the correct oriented answer. Finally, to conclude, there are 2 main takeaways. First, we propose a novel framework called Controllable Grounded Response Generation. Our experiments show how control and grounding can be mutually beneficial. Second, we introduce a novel inductive attention mechanism and show through qualitative and quantitative evaluations that this framework outperforms strong baselines for 2 scenarios where control phrases are provided by a simulated user or automatically predicted by a control phrase predictor. Interesting future investigations could be exploring various types of user-desired control other than lexical phrases, as well as extending the controllable grounded generation concept to broader generation tasks like document writing assistance. Thank you very much for listening.